Next one. So this is going to be a combustion reaction, and uh, you're going to have, this is similar to the one we did in the this slide show that we talked about how to set these problems up. Okay, so instead of octane, we're going to use pentane. So how many liters of oxygen gas is going to be needed to combust 50 milliliters of liquid pentane? And then how many liters of carbon dioxide are formed? And how many mils of liquid water are formed? The pressure is going to be 1 atmosphere, temperature 300. Okay. So kind of special about this one is that we have a liquid and we have a solid. I mean a liquid and not a solid. We have two liquids, not that one. We have two liquids, the pentane and the water. And we have a gas, two gases. Okay. We got two liquids and two gases. So, right, set up the balanced equation and then set up your table. Okay, so we're given the pentane, solve, and solve, and solve. Okay, so we want to figure out how many moles of pentane there are. Then we're going to figure out how many recipes from that, and then we'll bring that all the way across. Okay, there's no limiting because there's only one of the reactants. So do the math. So figure the density of pentane is 0.63 grams per mil. That'll give me 31.5 grams of pentane. And then multiply that by the molar mass. Divide by the molar mass, and which is 72 grams per mole. And so for there you have 0.4375 moles of pentane. Okay, find limiting. There's none, so you don't have to do that. So just determine amount of products and of moles of everything else. Okay, so figure out. So that's how many moles. Recipes you can do. For every recipe of pentane, you need one. Say if you have 0.4375, you can do that many times. So bring that all the way across. And then to figure out moles, you just multiply the recipes by the moles per recipe. Okay, next thing you do is figure out the amounts of the states. So for oxygen gas, using ideal gas law, so solve for volume. You have 3.5 moles. There's a universal gas constant temperature and pressure. So you will need 86.2 liters to combust all of the pentane. The amount of carbon dioxide you're going to produce, again, you use the ideal gas law because it's gas, just like this guy up here. Okay, moles from the previous slide, solve, and you make 53.9 liters of carbon dioxide. Okay, figure out the amount of water you're going to make. You make 2.625 moles of water. You need to figure out the amount of grams that is using molar mass, so multiply. And then to get mils, you divide by the density, and you get 47.25 mils of water. Okay. So pretty straightforward. Okay, again, this similar last one is you don't need to find limiting. So here's something that's kind of interesting, all right, is if you look at our answers of how much oxygen we produce and how much carbon dioxide we produce 86.2 liters. We needed, 86.2 86.2 liters of oxygen and 53.9 liters of carbon dioxide. Okay, so what's interesting is if you look at that ratio, 86.2 divided by 53.9, well, that's equal to 8 over 5, okay, which is the ratio of the two of the moles per recipe, okay. So we're going to see in one of the problems coming up is that we won't even have to, you don't even have to use the ideal gas law when you go from gas to gas, all right? Okay, when you go gas to gas, we could have just figured out the moles of oxygen, the liters of oxygen, 86.2, and then use this ratio, 5/8, to figure out how much carbon dioxide. Okay, so we didn't actually have to go through all of that, all right? So that's kind of cool things about gases. This is also known as Avogadro's relationship or principle. And it relates to Avogadro's law, which was N1 over V1 equals N2 over V2. Okay, you don't have to use this equation for this, but this equation here gives us this right here. Okay, because it says the moles, which is 5 over 8, has to equal the liters of 53.9 over 86.2. Okay, all right. So we're going to see how that goes.